So at the end of the last video, we were discussing the fact that we've been squashed in our dreams of achieving 100% efficiency of photovoltaic conversion. Very sad. This limit is stated and is material dependent as the Shockley-Queisser limit. And this limit is defined for a single junction material, so a material in which you expect to have a single band gap acting. And this limit has a series of contributions that basically makes so that you have a sequence of losses and a sequence of energies that you're not actually able to use for your photovoltaic conversions, or even if you use them, you lose them along the way. So the first concept to remember is that all of these calculations and tricks work on the basis that for one photon that you put in your material, you end up generating one pair. So one photon, one electron, one photon, one hole, but they go in a pair, so for every photon you have one electron hole pair, and that's it. You don't do multiple generations, just one at a time, and this is a very realistic limit because this is the type of interaction that you tend to have. So the first concept to consider is that given that you want to make something jump from the valence band to the conduction band and then conduct off in your material, you are not able to absorb any photon of which the energy is lower than this gap. So if your photon cannot actually breach the gap, is immediately lost and you cut it off completely. It's not going to interact in this business, it's off. This doesn't mean it cannot heat up your material. So this is part of the annoyance. It will still be interacting with your solid in a certain way, but it will not be absorbing. If you cannot bridge the gap, it's not going through. The second concept is that if your photon has an energy that is higher than the one of the band gap, it's still not the most efficient to be absorbed. So basically you could bridge the gap just because you go from lower down in the valence band to higher up in the conduction band, or even if you start here at the corner, then you go ballistics all the way up in energy in the conduction band. But still, this is not the energy that you can recover. The energy will always be at the corner of these potential things. So regardless of where you start, your electrons, as it starts conducting, it will lose energy and go back at the very edge of the conduction band. So this effect here is again a thermalization effect. It's energy dependent. So if you shine a lot of energy that is higher than the band gap on your material, it will photoconduct. You will have a photoconductivity effect, but all the energy, all the extra energy that you put is not going to be used for electronic effect, is going to be used for heat loss. So again, you will heat up your material and it will photoconduct, but this is not the most efficient way. You're shining a lot of stuff and it's lost. The other concept that you need to consider is that to be able to, as we were saying, to be able to conduct this electricity out of the junction instead of just making the effect and let it stabilize off by itself, you need to have contacts placed on your material. And every point of contact is a point of slight friction, like there will be a slight voltage. It's a bit difficult to pass from one side to the other. You need to go into a different material. This is a loss of voltage, because to be able to do this jump, your electron will have to go through something. So in comparison to the potential that you had at your edge of valence and conduction band, which is the actual voltage that you want to be able to pull out of your photocell, you will have drops. So you will go off to a slightly different voltage. So if you wanted the maximum voltage of 0.7 per photocell, you'll probably go lower because you need to have contacts, and the contacts will mess up how much your electrons are capable of doing it if they actually need to go somewhere. And then you have another concept that is unfortunate but unavoidable, which is you can recombine the pair. So we've been saying that you want to drag the pair apart from each other as soon as possible. So you want to split your electron away from your hole and bring them on the other side of the junction as soon as possible. But statistically speaking, some of the carriers will recombine. So it is not true that you will have one photon, one pair. It will be slightly less than one photon for slightly less than a pair. So you might need more photons to statistically generate a pair or something like that. But you cannot consider that for real every photon will result in an electron to conduct somewhere. Some of these electron hole pairs will just recombine and call it a day, and there will be nothing to be known about it. So this is something that you have to consider. Thermodynamics works this way. So what if we want to go beyond the Shockley-Queisser limit? What do we do? Now, when we actually talk about solar cells, we talk about using our sun. We have our sun shining on us. It's virtually free energy. We're not commanding the sun. We don't have to turn it up. It's just there shining on us. We want to use everything. Ideally, we would like to use all of the energy that is given to us by the sun. So how do we maximize the efficiency? We should make sure that we do not waste all of this light. Because the issue that we are having here is that you're shining a spectrum of energies. So the actual radiation that comes to us from the sun is this whole thing that you see here in yellow. And this is very close to what you will compute as a black body radiation. So in fact, the Shockley-Queisser limit was first developed with a black body radiation, and afterwards corrected with the fact that the sunlight is not exactly a black body radiation. And then a future correction should be made on the fact that you don't have your solar panels. In some cases you do, but usually when we use them on Earth, they are not out of the atmosphere, they are at sea level. So the light at sea level actually has this distribution that you see here in red. We can discuss afterwards when we do our interactive session what are these drops, because you can see that there are very sharp drops in which you don't see any sunlight. You can tell me what are those. But the fact that we want to maximize the efficiency means that we want to use all of this red part. So anything that is in red, we would love to be able to grab it and convert it. Now, the issue is that, as we were talking about, the Shockley-Queisser limit is a thing that comes up for the fact that you have a single junction cell. And as we were saying, the optimal working of the junction is at the right energy to bridge the gap. So ideally a single energy. You could deviate a bit because you can live with like something slightly higher that will result in a slight loss. You know that if it's lower, it's not going to be absorbed. So if you have a band gap of 1.6, for instance, which is here, 1.6 electron volt, and you shine 1.7, 1.8, 2, you will still absorb the photon with lower efficiency because you will lose something as heat. But if you shine 1.5, that thing is lost. So this limit of efficiency comes because your material is limited in terms of band gap. You have a band gap per material, you cannot change the band gap of the material, it's there. And if you want your material to stay there with that band gap, you know that you're limiting yourself to a range of energies. The fact that every material has its own band gap, though, means that you could potentially tailor the level of materials to actually have the optimal sequence of absorption. So you could have multiple materials with multiple band gap optimized to work at different ranges. And imagine if you were to have a top material that absorbs at 1.8, then anything that is from 1.8 higher gets cut off because it gets absorbed by that material. Call it a day, off. Anything that is lower than 1.8, so imagine you are here at 1.8, everything that goes lower, so all the rest of the light passes through. You catch another material that is at 1.4, anything that is between 1.4 and 1.8, because 1.8 was absorbed before, will get absorbed by the second material. And everything that is below 1.4 will again pass through the junction because it won't see any reason to get absorbed. And then if you have a bottom material with 0.6, it means that anything between 0.6 and 1.4 actually gets absorbed. Now, technically speaking, you could layer this as much as you want to make sure that you have the interconnection. The light that gets transmitted from one point to another will get absorbed by the second band gap. And you cut off different energies depending on how do you layer, right? So you want to make sure that your layering takes into account the sequential absorption sequence, but this will actually allow you to take advantage of the full spectrum, because depending on where you cut with your band gap, so the first light that you put in is the full distribution of the sunlight at sea level, then you cut this off, then you have this spot left, then you cut this off, then you have this one left, then you cut this one, and you have this one left, and then you cut this, and then there will be some light that you're not able to absorb, but you can live with that. This means that you go beyond the Shockley-Queisser limit for one fundamental reason. You're not using a single junction anymore. It's like layering sequential photovoltaic modules that work all with the same light. So for one point of irradiation, you have a sequence of photons, they come in at different energies, you start to absorb them, but instead of wasting everything that is not at the right energy of the band gap, so if you have just this layer, anything that is below, it's gone, you cut and you use all the rest. This will significantly increase the efficiency of your module because you're not wasting the sunlight. This is exactly the concept that is used in the third generation solar panels, so the most efficient one that you can possibly have, which are multi-junction solar panels. So what you want is a cake. You want a series of layers of different materials with different band gap ordered nicely for the type of light that you're expecting. What you want are like something that is like high level for type of technology that you want to be able to put in. So you want this thing to absorb light at a high rate, because of course you don't want to waste any light by not being absorbed even though you could. So you want to make sure that if the photon is at the right energy, goes in, actually does the photovoltaic thing. You want the carriers to stay alive as long as possible. So when you generate your electricity carriers, they actually stay there, they do not recombine, they travel through, and they travel too nicely because you have a nice mobility. And since you want to cake them up, and we saw that the higher mobility of the carriers is actually possible when your material is a single crystal, you want to make sure that you're able to layer a sequence of single crystal materials, one on top of the other. Now, this is possible if the materials are close enough to each other that, yes, okay, we are a different material, but we don't brutally strain against each other. It's not really like putting wood and metal on top of each other. And this is often possible for semiconductor because, as we've seen, they tend to have alloys with a similar crystal shape. So if your lattice on one side is this big and the lattice on the other side is this big, this is lower, but still when they meet each other, they can sort of match and do something. If you have one that is this tiny and one that is like this, when they meet at the junction, the lattice is not compatible, so you could still try to have something uniform, but the material will likely strain in between, so it won't be a perfect junction. If you put an imperfect junction, then any type of mobility that you want to try to have in between, because you're trying to move things around the depletion zone, will be hindered. So the more compatible, the better it is to layer them up. And this is also good because you want to be able to do sequential doping as well of your material. You need to remember that the point is not just the cake of your semiconductors to make p-n junctions, but also the contacts. You cannot conduct electricity without the contact. Any contact that you put on your material is one less surface that is exposed to light. So if you cover your materials in contact, then all the electricity will actually go better, because the more conductive surface there is, the more outcome there is for the electrons to go somewhere else. But you reduce the surface that is exposed to light. If you expose a lot of the surface to light, but then you have like two teeny tiny contacts on the side and nothing else, you likely waste a lot of the carriers because they get recombined and they stop moving before they can do anything else. So you need to optimize these things, and the metal connection need to be optimized to do this trick properly. And the last thing that you need to have when you do this caking is making sure, since again you want to be able to get to the contacts, that your electrons can actually go through as unhindered as humanly possible. So when you have the layers of your p-n junctions, and different junctions have different points of depletion zone in which you're actually generating your carriers, you want to make sure that there are points in the junction in which the electrons can just pass through with virtually no resistance, which will be a tunneling point. So this is the point in which you actually use that trick of layering the p-n junctions differently from just p and just n, and when you do avalanche type of tricks. Because then you avoid, instead of having just the p and the n, when you look at the materials that we have in this layer, you have points that are very highly doped, and depending on how you dope them, it means that the passage in between is unhindered and incredibly fast. You create tunneling because you have that super strong potential. The electron will just see the passage through and will get unhindered by anything else. But the concept remains fundamentally the same. So you have your p and n doped material, and depending on which materials you're involving in this business, you can change the band gap. So here you have this aluminum indium phosphate mixed with gallium indium phosphate, and this creates a p-n junction with 1.9 electron volt. Then you can see that there is another point of junction that is fundamentally a tunneling point, in which you make sure that any electron generated here can actually go through there to the contacts. The middle cell is your point of 1.4, so anything at energy higher than 1.9 gets absorbed here. Anything with energy 1.5 to 1.9 gets absorbed here. Then you have another point with another tunnel junction, in which you have your bottom cell at 0.66 electron volt, so anything between 0.66 and 1.4 gets absorbed down here. Anything that is below 0.6 is not absorbed, it just doesn't go through. You lose that energy because there is nothing able to absorb it. And you have your point of contacts, meaning that the electricity will actually get generated but get off following the bias that you imposed. Now this would be amazing, but the question is, why are we not using them constantly, since the idea is so good? It would be super amazing because it means that with infinite layers, and if you layer them properly, you could bring your top efficiency to 87%, which is insane. It's an incredible amount, given that we were discussing, we have this strong limit at 33%. 87 it's a completely different business. This is huge. But 87 requires a sequence of layering, and the more stuff you want to layer, the more becomes challenging to have the tunnel junctions, to have actually transmission of lights that doesn't get absorbed. So the current efficiency of solar cells is actually a bit above 40%, but not 80, certainly. And you can already guess what is the problem here, that this thing is incredibly pricey. These are not as silicon monocrystalline single cells. These take a lot of money. Bringing them up, layering them up, making sure that the connections are nice and steady is difficult. The materials to begin with are more pricey than what you will have with silicon single crystal. Doesn't mean that they are not used. At the moment they are used for high level purposing. So for instance, the Curiosity rover had the triple junction solar cells like this with 40% efficiency. Why? Because you put your rover in a position where if it doesn't convert as much light as humanly possible, it doesn't have electricity to work with. So it's a good point to actually throw this thing in. But even the Curiosity rover with this amazing multi-junction gallium arsenide system had some issues, with meaning that you will have a drop of efficiency because you are in real life situation, and real life situations means that your panel is saying something that is not just you trying to measure the output. In particular, Mars is dusty, and these are solar panels, and the Curiosity rover actually had the solar panels all over the place. The solar panel will get dusty. If they get dusty, then the area on which you actually shine the light gets modified. If it gets modified, the efficiency drops. This brings us to the final point, which is actually optimizing your solar panels with additional stuff that is not just how good is your material, because your material in your thing is in between. So at the moment we've been discussing solar panels arrangements just on the basis of this is the material, this is how efficient it is, this is how we go, call it a day. The only other thing that we touched upon was the efficiency of the contacts. But you do not want to use just that. You might want your material to be protected, because if you degrade your material to begin with, you do not use your solar panel. And as we were discussing with the Curiosity rover, you might actually want to be sure that it doesn't get dirty, because dirty solar panel means less light conversion. But there is also another issue, which is, as we were saying, silicon is dark. And by being this dark, it means that there is a reflection of the sunlight. So you want to absorb sunlight, but sunlight hits and then gets reflected off. And dirt and were susceptible. So you want to cover them, but you don't just want to cover them. You actually want to cover them in a very specific way, because you could just put a layer of glass of an arbitrary thickness that is good for you, and this will already improve how nicely your silicon is able to operate, because you tweak the reflection already. But since reflection is a very physical trick, you can tweak the thickness of your glass to make sure that at the right wavelength in which you want your material to operate, you are not reflecting the sunlight off. So the bare silicon, you can see that it has a 30% of reflectance, which will already take off a very significant amount of the light that you want to use. If you put an optimal thickness glass on top of the silicon, you can virtually use all the sunlight that passes through. This is because basically the quarter wavelength thickness is something that you can optimize to avoid this reflection effect. So there will always be something that gets reflected, but since, like, given how reflection works, it's basically a concept of what interference are you letting pass through. So if the thickness of your glass is tweaked against the wavelength of the light that you want to pass through, the glass will be perfectly transmitting of that wavelength specifically, and then all the others instead will get reflected off, because the thickness, like the reflection, actually works with where are you touching your glass and how thick is your glass with a certain reflective index. And depending on where you touch your wavelength in terms of interference, you get reflected off with a certain percentage or not. What you want to have is the perfect transmittance for the right wavelength, and you can see that it cannot be the perfect transmittance for every wavelength. Even when you optimize the anti-reflection coating, you still see a huge reflectance of other sunlight. This is not necessarily bad, because you actually might want to reflect off any sunlight that you're not going to use for your solar panel, because anything that your solar panel gets hit with and does not absorb results into heat. So this is already a nice optimization that actually lets us work through a lot of stuff. Going through the concept of reflections, in combination with this anti-reflecting coating, you might want to think about how do you texture your solar panel, because your issue is that if your solar panel is perfectly flat, even if you have incident light at 90 degrees, which is optimal, you still reflect off a certain percentage. But if you have a texture in your surface, it might mean that you get incidence, part of absorption, part of reflection. The part of reflection will still get another layer of the material to hit, and then another part will get partially reflected, but it will be significantly lower than what you will have with a steady surface. So if you manage to texture, then you have more surface available to actually interact with light and make sure that all the light available gets into the material and not out of the material. But how do you actually texture something with something like this when we talk about the fact that this is a single crystal? This is a good point of using solid materials, because if they are crystalline, it also means that the symmetry, as we were talking about, of the arrangement of the atoms in your material makes certain atoms more susceptible than others to chemical reactions. So if I were to tell you you need to texture the single crystal by hand, you will tell me that I'm insane. What do you do? Do you like sandpaper it off until it's a nice steady pyramid exactly like this? Do you use a laser? This seems like a huge effort. But when you actually treat single crystals of silicon, and not even just silicon, a lot of other materials like this, with acid, with of course the right timing, the acid will attack preferentially certain layers of atoms in comparison to others, while keeping the rest of the single crystal intact. So this effect of making pyramids or staggered pyramid is created inherently by the chemical reactivity of the material. You just put your material in acid, you will get out your material with spikes or pyramids, depending on how do you actually apply your acid, because the acid will corrode the material, but it will preferentially start to corrode it in a certain specific crystallographic direction. So you will make a crystal that is heated up in a certain direction, and this will be super precise, and then you can add stuff on it. So it's a very nice, easy way to do stuff that really improves your business. Additional optimization that you can have, final point, is that first of all, not only you can stagger your material as we were discussing, but you can make sure that instead of having incident light that goes 90 degrees and that's it, and everything that doesn't go 90 degrees has a lower probability of getting absorbed, you can first of all focus your light Now, you might have noticed that solar panels are never installed around flat on the ground, just because this is a very bad idea. The best way to angle a solar panel is actually with 10-15 degree of angle, just because you don't have a nice sunlight all the way through. You want to absorb most of the sunlight when the sun is at the zenith, because at the zenith is the highest output of energy that actually goes like onto something. So if you have it tilted in the optimized direction, you already optimize how much sunlight you're able to get before the sun goes down or up, but you are in the right point. And also you want to add an additional focusing, so that when the sunlight hits already at an optimized angle, you have a bent surface, and this is called concentrators solar cells, for which you basically have a series of mirrors, or your material might be already bent by itself, and you start to focus the light on your solar cell. So instead of relying on the fact that something statistically will get absorbed, you focus with lenses and then you hit the solar panel. So you have focused light on a texture surface with anti-reflectance coating, with possibly optimized arrangement of the p-n junctions. You can really push off the limit of the Shockley-Queisser. This is how we got to the best performing solar panels currently available. This is the last updated NREL like outcome of all the solar panels in every possible configurations, in every possible arrangement available to technology to date. And you can see that the best performing solar panel is currently a Multijunction solar cell. This is, I think this is a triple junction. No, this is a 4 junction, for 4 or more, with concentrator. So it is doing the concentration 4 junction, and it's almost at 50% efficiency. So this is already pushing the limit that we were discussing on the Shockley-Queisser. You can see that the single junction solar cells are more down here. So you, even with all the improvements, you can see that they are below the 33, which is the limit considering the full surreal optimization of thermodynamics. This is a hard limit, and the best ones are the crystalline solar cells. The thin films are some of the things that we were discussing before, even some of them with a concentrator. But you can see that there is a sequence of red ones that we didn't quite discuss, which are emerging photovoltaics with slightly different technology, still the same concept, but slightly different materials used. And this thing will be discussed in the tutorial versions. So this is the concept for the week, and the sequence of learning objectives that I want you to be comfortable with if we end up discussing them afterwards. So when you look at these questions, you should be able to answer it yourself with confidence. And I would advise you to leave any questions of doubt or super big question marks on the feedback-free document. I will see you on Tuesday for the plenary session in which we actually discuss this content in person. See you soon!